And of course, using equation 1, excuse me. Using equation 1, we can rearrange it and solve it in terms of V to determine V naught. So this also implies that if we know V, then we can write V naught can be equal to V into RT plus R3 over RT. And remember, RT is a thermistor. This will be used to design the circuit so the output does not vary as a function of Vt, which is temperature dependent. But I'll just be using equation 2 or equation 1. Now let's determine V as a function of the VBs of the transistor. So I'll start at point A, the base of Q2. It's not very clear. This is the point A. The emitters are point B. And this is point C. The base of Q1 is point C. So if I start at point A, I go against the potential VBE2. So I can write, apply KVL to loop A, B, C implies that minus VBE2 plus VBE1 should equal to V. But what is VBE2 in terms of Ebermole's voltage current relations for the transistor? We've already done it, so I'll just give the result. So this is the same as saying minus neta Vt natural log IC2 I02 plus neta Vt natural log IC1 I01 is equal to V. So next, let's simplify equation 4. So this can be written as, equation 4 can be written as I'll start with the positive term. Neta Vt, which is the second term, natural log IC1 I01 into I02, IC2, it's equal to V. Next, we can say that for my transistors, so for my transistors, the saturation currents are equal. So 5 can be written as neta Vt natural log IC1 divided by IC2 is equal to V. So next, we have to find IC1 and IC2 in terms of the circuit parameters. So we can say, but IC1 is equal to, and IC2 equal to, so you go back to the circuits. So if you look at the circuit, let's start with finding IC1. IC1 is the collector current of the first transistor. So in this circuit, this is your IC1. And this current over here will be your IC2. Now let's determine IC1. Now, since the positive input of A1 is grounded, it means the negative input of A1 is a virtual earth, and therefore the current that flows through resistance R1 is nothing but VS1 divided by R1. So this current that flows here is the same as IC1. And similarly, for the second transistor, if you look at the input of amplifier A2, the positive side is grounded, and therefore the negative input of A2 is also virtual earth. So it's like the collector of Q2 is also virtual earth, and therefore the current IC2 is the current that flows through the resistor R2, which is just VS2 divided by R2. So we can substitute for these values. So IC1 in fact is VS1 over R1. Let me just put this other one here so you got more space. And IC2 will be equal to VS2 divided by R2. So let these results be called 7. So from equation 6, we found out what is IC1 and what is IC2 in the natural log. So let's substitute these results in equation 6. Let's substitute result 7 in equation 6. So if it's if we substitute that, we'll get neta Vt natural log of IC1. IC1 is Vs1 over R1 divided by IC2. IC2 is Vs2 over R2. So sorry. I think I'm taking too many shortcuts. Let me remove this. So I've just repeated myself over there. Here is okay. So we're just substituting results of 7 inside 6. So any one of the equations is sufficient. So to prevent confusion, let's just rub one of this. I think that's okay now. So we just substitute the results of 7 inside 6 for that. So we determined what V is. So now knowing V, we can determine what the output voltage is. Now from, I think, equation 3, or from equation 2. From equation 2, V naught was equal to V into brackets RT plus R3 over RT. Or you can write maybe 1 plus R3 over RT too. So we can say from 2, you can say, but from 2, V naught was equal to V into, I think it's R3 plus RT over RT. Let me just check again on that one. Okay, I've written the RT first. RT plus 3, R3 over RT. Okay, it's all the same. This is from 2. So if we sub 8 and 2, we'll get that V naught is equal to, instead of V, I'll put the whole expression 8. So I think I'll start with the R3 plus RT over 3 first. Then V is neta Vt, and natural log. I'll put in this form, Vs1 over Vs2, R2 over R1. Next, we can say that if Vs2 is fixed, then we can write that V naught convolution as RT, or 1 plus R3 over RT into neta Vt natural log of K Vs1, where K is equal to R2 over R1 into Vs2. So this tells me that this circuit performs log computation. So this circuit performs log computation. So this is a log circuit. For a log amplifier. Where K can be varied. With a second voltage Vs2. Can make the design easy by making R1 equal to R2. So K will just be 1 over Vs2. So this is a log amp, which the scalar K can be varied, the second voltage Vs2. So if, for example, if it's a circuit that performs compression, you can vary the compression rate, which can be very useful in some circuit applications. So, so I hope everybody has understood. how we got into this. I'm seeing somebody is no. So is everybody okay? We can move to the next. Everybody has copied? Anybody who is not copied, you can just switch on the mic. Moses, have you taken everything?
Yes.
So I can move on, eh? Because you people are not.
Yes, we can get to the next.
Okay. So now you can do the rest. So the second question is this one. Very simple. The next is this one. Now this for the boys. So just do this correction over here in the circuit. So this is circuit, we just got 2 inputs. 3 inputs, in fact. So find the output for this circuit. It will just be using the principles we designed. So the next topic is the analog multipliers and dividers. Analog multipliers and dividers. But the crux of this topic will be analog multipliers, because the dividers are just derived from the analog multiplier. Now, apart from the microprocessors and microcontrollers, I think the analog multiplier is one of the other very useful electronic circuit. Without it, there will be no long distance communication. Because in long distance communication, we need modulation techniques. And most of the modern modulation techniques use multipliers. Be it your FM, AM, phase shift modulator, QPSK, SSB, DSB. All those circuits require an analog multiplier. All these computer modems, they all require analog multipliers. Now, from the basic definition of an analog multiplier is what I've written here. An ideal analog multiplier is a circuit whose output is a function of Vx and Vy, such that V naught is Vx, Vy divided by some scalar k, or V naught is some scalar into Vx, Vy, where k's are constant. So any circuit whose output takes this form, where Vx and Vy are the input voltage variables, is referred to as a multiplier. The symbol of the multiplier is what I've drawn over here. The symbol of the multiplier is what I've drawn over here. It's normally a part rectangle with a triangle on top and an output. Where the two inputs XY, we apply the voltages Vx, Vy, and the output V0 is some scalar K into Vx and Vy. Now, an ideal multiplier has the following characteristics. Number one, it should have an infinite input impedance to the signal Vx and Vy. So the input signals are the inputs Vx and Vy, i.e. it should not load the inputs. The other requirement of an ideal multiplier is that it should have zero output impedance. Of course, all electronic circuits, you'll have an internal resistance, normally we call R0 inside here, which you normally call R0. And the voltage generated in the input and at the output, part of it is lost inside R0. So if the output impedance is zero, then all the voltage generated inside appears at the output of the load. So point number two is zero output impedance. Number three is that it should have an infinite bandwidth. It means it can multiply signals from a very low frequency, in fact, starting from DC to an infinite bandwidth. And then it should be linear. The output should be linear for all ranges of the input. I.e., if we supposing we set Vx is equal to 1 and Vy changes from 1 volt to 10 volts, the output should be linear. It should not change. Now, practical multipliers have the following limitations. Number one, since the power supply is usually plus minus 15 volts, the theoretical maximum output voltage swing is limited to plus minus 15 volts. But for normal operations, it's usually restricted to plus minus 10 volts. This one you get from the data sheet of the manufacturer of the multiplier. Of course, since you have transistors at the output, when the transistors saturate at the output, there'll be a loss of about 0.2 volts for silicon. So even if the supply voltage is 15, the maximum voltage, it will go close to 15, will be maybe 15 minus 0.2 volts. But the manufacturer will normally tell you, don't use that, use maybe 10 volts as the maximum output on the positive side, and minus 10 volts on the bottom side, because the supply itself is 15 volts. Next, the input signals are usually limited also to plus minus 10 volts. So Vx and Vy are usually limited to plus minus 10 volts. They also have a limited output current capability. This IC multipliers cannot give an infinite current. We're limited. Of course, the transistors at the outputs over there, and transistors cannot pass infinite current. Also, they have an output impedance which is not zero. So the load that should be used is large. So if you want all the voltage generated inside the output of the multiplier to appear to your load, you've got to make your load resistance large. So I should put here IE use should be this way, large load resistance. Okay. Whoa, what's happened? I use a large load resistance. So that all the voltage generated at the output, because for example, this is what I mean. If this is R0, this is the output of your op amp, this of your multiplier rather, and this is your load. You want all the voltage appearing at the output. Okay, so if your generator voltage, then V0 is RL Vg over R0. That's RL. So if you want all the generated voltage inside your multiplier to appear at the output, then RL should be much, much greater than the load resistance. Typically, the load resistance will be maybe 50 ohms or even less. Then also, these multipliers tend to suffer from offset errors, as we shall see, because of their construction. They use a lot of differential amplifiers inside. And we know differential amplifiers suffer from offset errors. And finally, they have a finite bandwidth. Now, bandwidth depends on the transistors which are used inside the multiplier. So if you use high frequency transistors, you'll be able to multiply up to gigahertz, a few gigahertz. So these are some of the practical limitations of real multipliers. Now let's see how we implement multipliers. So this will be called practical realizations or practical schemes of realizing multipliers. So the first one is called the log anti-log method. We'll be using log circuits and anti-log circuits, which we've just studied. The second method is to use what is known as the quarter square technique. Which we shall see later on. And the last method, which is the method that is used by most in the industry, is the transconductance or the variable transconductance multiplier. It's now referred to as variable transconductance multiplier. Or sometimes they just write a transconductance multiplier. So these are the schemes that are normally used. So let's start with the first method, which is known as the log anti-log method. So in the log anti-log method, we make use of this relationship that XY is anti-log of log X plus log Y. So to implement this multiplier, if if I start with my variables, say x and y, which I want to multiply, so I'll have to go through a log amplifier. And the first output will be log. So this is a symbol we normally use. So you start with 2 log amplifiers. So the first one will give you an output which is log x. The second one will give you an output which is log y. And then these two will go to antilog. So you get xy. So we studied these circuits in the earlier topic, and you can see to design a good log amp requires very many op-amps, and op-amps suffer from offsets. Okay, and most of the multipliers we've designed, they are just the ones which only compute the log of a current flowing in one direction. So for your assignment, go and find out how you can modify the circuits that we've studied so far, both log and anti-log, to be able to compute the anti-log of not only a positive variable, but also a negative variable. So in this scheme, we use the relation that anti-log of log x plus log y is xy. So the circuit implementation is what I've drawn over there. You need 2 log amplifiers, you need 1 anti-log amplifier. And it has got so many components inside, so many op-amps, so many offsets to deal with. And therefore it will have the following limitations. Number 1, it will be high cost because many op-amps are used. It will also be complex. And then number 2, log and anti-log amps are usually unidirectional, meaning they compute the logs only for current going in one way. And unidirectional op-amps, actually I should not write unidirectional op-amps. I should write unidirectional log and anti-log amps. Unidirectional, not op-amps. Unidirectional log and anti-log just in short form, amps. Log and anti-log amps are usually expensive due to the large number of components, due to the large component count of the log and anti-log, amps. Also, number 3, the dynamic range of the input signal is usually small in the region where the log, or we can also add anti-log, where the log and anti-log is computed with high accuracy. Next, the bandwidth is small and dependent on the op-amp used. Now, different op-amps, when we're studying even our op-amps, the 741s earlier on, there are different grades of 741s. There are 741s for do-it-yourself applications. There are 741s for even military applications. And there are actually 3 categories: industrial applications. Okay, so those ones will tend to be more expensive and rare. Will you find them in the shops? Say like in Nairobi over here. Okay. And therefore the bandwidth will also be different. The bandwidths will also be different. But since you've got so many op-amps cascaded, the bandwidth will tend to be small. So using op-amps, it's rare you'll find even an op-amp that can work up to, say, 50 megahertz using this technique. Then finally, they suffer from large offsets due to the devices being used. Because we've seen the internal construction of op-amps. We suffer from offsets. You have to use null offsetting circuits. And therefore, this circuit, actually I should not read circuit, let's call it this scheme of, this scheme is rarely used. What scheme? The log anti-log method, also called the log sum, because it's like you're adding the 2 logs and then getting the anti-log. So we rarely use this scheme. Just for academic purposes, using this mathematical equation. Now the next one is called the quarter square technique. The other way to implement an analog multiplier is to use what is known as the quarter square technique. This technique was used in the early 60s. If you go through it. So the quarter square technique, I'll just introduce it because time is not with us, uses this identity that 1/4 into brackets x plus y squared, where these are the voltage variables, minus x minus y all squared is equal to xy. So if you expand the left-hand side, you'll get it equal to xy. So if you use this identity, you can see in these brackets, we need adders for pluses, x plus y. We need subtractors, x minus y. And then we need squarers to perform the function x plus y squared, and also x minus y squared. So this is the block diagram of the implementation. Okay, so I'm not put the voltages there, but you'll have an input voltage here, y, x. So the output here will be x plus y. Then you put a squarer. So here you get x plus y squared. And also we start at the bottom over here. We have the input variable y, x voltage. So here you get x minus y. So here you get x. So this is a squarer, x minus y all squared. Then you subtract the first from the second. So over here, you're going to get x plus y all squared minus x minus y. X minus y all squared, and then you multiply it by a quarter. So the output over here will be 1/4 into x plus y all squared minus x minus y all squared. And if you look at this equation, this is actually equal to xy. So in this implementation, known as the quarter square method, because you can see there's a quarter times into the brackets x plus y squared minus x minus y squared. So in this method, the circuit elements required are squarers, adders, and subtractors. And here we use diodes to perform the squaring function. Now, when you study the op-amps, it's very easy to understand how to make an op-amp to add, how to make an op-amp to subtract. Okay, so that is what you're going to use. So this is the circuit implementation. This is the circuit implementation. You got your input variable x here, input variable y over here. So in the next class, we'll go through this. So these are the diodes D1, D2, D3, D4, which performs the squaring. Now for analysis, I'd put some values over here because this is an op-amp. Input is connected to the negative, feedback resistance R, input resistance R, so the output of the op-amp here is minus X. And this other input over here, if you follow it, it goes to the output of the second op-amp here, whose input is Vy, the circuit is the same, so it will be inverted. The output of the bottom op-amp is minus Y. So minus Y goes up over here through these two resistances of 5K, 5K. This is for adding before going to be the forward current of this diode D1. So I think in the next class, we'll go over this because I think time is up. We can't, but this is the other technique which is used to perform analog multiplication. As you can see, we're using op-amps. You are going to use diodes to perform the squaring. We shall see how the diodes perform the squaring. But since you can see op-amps are cascaded, op-amps are quite slow. Op-amps suffer from offsets. This is just academic. No company is going to build anything like this. Okay, but it's there for academic purposes. So any questions on this? Any questions on this? Any questions on this? So I think we'll stop over there because time is not with us. So thank you, everyone.